Welcome to The Explainer. Listen, today we're doing something really exciting. We are heading miles and miles underground, deep into the Earth's crust, to unpack the totally mind-boggling fluid dynamics of oil extraction. We're digging into some fantastic source material on fluid properties and two-phase flow in oil reservoirs. So if you've ever wondered how on earth engineers manage to coax oil out of solid rock under literally extreme conditions, you are absolutely in the right place. Let's get right into it. Okay. To kick things off, let's dive into this core question. What actually happens when you open a shaken soda bottle 10,000 feet underground? Now, this isn't just a trick question. It's actually the perfect metaphor to help us understand the intense, real-world physical challenges of reservoir pressure. Just imagine all that trapped energy, the extreme compression, and then that sudden, violent release of gas. That is exactly what reservoir engineers are dealing with every single day, just on a massive subterranean scale. So let's start with Section 1, the underground soda bottle, understanding the pressure threshold. To really grasp oil extraction, we have to understand the initial status quo. Deep underground, you've got a pressurized, perfectly closed bottle made entirely of rock. Before a well is even drilled, everything down there is in a very delicate balance. And the absolutely crucial starting point here is the bubble point pressure. This is the exact pressure at which dissolved gas first breaks out of the liquid oil to become free gas. Going back to our metaphor, this is effectively the precise moment the cap twists off our underground soda bottle and you hear that hiss. As long as the pressure stays above this point, the gas is perfectly content to stay completely dissolved in the oil. But the second the pressure drops below it, tiny gas bubbles begin to form.
And this gives us a night and day difference in physical states. Just look at the contrast. In an undersaturated reservoir, the pressure is still high. It's above that bubble point. The gas is totally trapped and dissolved. But in a saturated reservoir, the pressure has dropped, and suddenly, free gas has broken out and is now coexisting with the oil. Once you dip below that bubble point, the fluid behavior completely, radically changes. You're no longer dealing with a simple liquid. You are dealing with a highly volatile mixture.
Which brings us to Section 2, changing fluid physical properties, or as I like to call it, tracking the mathematical mess. Because once that gas starts bubbling out of the oil, man, the physics get incredibly complicated. Engineers can't just guess how the fluid is going to behave. They need rigorous math and PVT, that's pressure, volume, temperature, properties to track the changing nature of the oil and gas. What's really fascinating here is how we can treat these dense mathematical variables almost like characters in an unfolding story. First up, we have BO, the oil formation volume factor. As pressure drops below the bubble point, BO decreases. The oil is literally shrinking as it loses its gas. Then you have BG, the gas formation volume factor. This one increases non-linearly because the gas is expanding rapidly. And finally, RS, the solution gas-oil ratio, decreases simply because those bubbles are actively escaping the liquid. Watching these variables shrink, expand, and escape gives us a perfect mathematical picture of the chaos happening underground. But there is a massive real-world consequence to this changing math. Losing that gas makes the remaining oil significantly heavier, denser, and way more viscous. Based on the foundational correlations by Beggs and Robinson from our source material, as those lightweight gas bubbles escape, what you're left with is something called dead oil. It becomes thick, sluggish, and incredibly stubborn. It's kind of like trying to suck a really thick milkshake through a tiny coffee stirrer instead of just drinking a glass of water. But remember, where this is happening, it's inside the microscopic, highly restrictive pores of solid rock, which leads us to a major underground crisis. And that triggers Section 3, the rock traffic jam, where fluids are competing for space in the reservoir. Let's just walk through exactly how this traffic jam forms. Step 1. Initially, the oil flows freely through the rock as a single, high-pressure liquid phase. Everything is moving smoothly. Step 2. The pressure drops below that critical bubble point we just talked about, and the gas bubbles out, instantly expanding into that microscopic pore space. And then step 3, boom, we have a bottleneck. That newly freed gas physically blocks the oil. The gas is lighter, it's faster, it's taking up all the lanes, drastically choking the oil's flow and heavily reducing the rock's permeability. Which brings us to a really vital distinction that engineers have to make, contrasting absolute permeability against effective permeability. Now, absolute permeability is what you might measure in a pristine laboratory. It's the rock's static flow capacity when you've only got one fluid present. But out in the real world, it's a totally different story. We have to use effective permeability. This is the severely reduced flow capacity for oil when it's actively fighting for space with that expanding gas. If an engineer only relies on the absolute lab data, they're
their production predictions are going to be disastrously wrong. So, with the oil shrinking, getting thicker, and getting stuck behind expanding gas in this microscopic traffic jam, how on earth do we actually get it out? Well, let's look at Section 4, Predicting Complex Well Flow, and the engineering solutions we actually use.
To figure this out, engineers use something called an inflow performance relationship, or an IPR graph, to predict flow. And notice the stark difference here. For single-phase flow, when it's just oil behaving nicely, the graph is a beautiful, predictable, straight line. It's really simple math. But once we enter two-phase flow with both oil and gas, that straight line just goes completely out the window. We have to use Vogel's correlation, which results in a curved, nonlinear graph. This curve visually accounts for all that gas interference and those changing fluid properties we just explored.
Now, we all know a well's pressure isn't static, right? It drops over time. So engineers cleverly combine these ideas into the generalized Vogel inflow performance model. This is brilliant because it hybridizes the math. It generates a straight line for the early days of the well when pressure is super high, well above the bubble point. But the absolute moment the pressure crosses that threshold, the model switches seamlessly to Vogel's curved equation. And by drawing on the foundational logical framework of an engineer named M.B. Standing, this approach allows us to accurately predict a well's behavior across its entire lifespan.
But hey, what happens when the real world doesn't play nice with theory? Because sometimes Vogel's correlation just doesn't match the actual field data. Enter Fetkovich's approximation. This is a highly adaptable alternative. Instead of Vogel's specific curve, Fetkovich normalizes the equations using the difference in pressure squared. To actually make it work, you just test the well at two different stabilized flow rates out in the field. This gives you the absolute open flow potential and a very specific exponent, N, which effectively lets engineers custom fit the math to the specific, weird quirks of their exact well.
All right, we've covered the physics, those underground traffic jams, and the complex math, but I want to leave you with a real-world dilemma straight out of the source materials problem sets. Imagine you're an operator. How do you balance high immediate production, getting the oil out fast and cashing in on high pressures, against the very real risk of bleeding off all your gas too quickly? Because if you drop the pressure too fast, you lose your gas drive entirely, and that thick, dead oil we talked about gets trapped underground literally forever. It is a massive financial and physical balancing act. So definitely think about that the next time you pop open a shaken soda bottle. That's all for this explainer. Keep learning, and I'll see you next time.